This tutorial is an introduction to bivariate association and measures of association for variables measured at the nominal level. Measure of association. It helps us trace causal relationships among variables. It is the most powerful tool for measuring and analyzing cause-effect relations. It measures strength and direction of a relationship between variables. It is used for purpose of prediction. If an association is existent between the two variables, we can predict from one to the other even if the variables are not causally related. For example, predicting a score of one case through the score of another. Limitations of measures of association. These statistics cannot prove that two variables are causally related, despite the existence of a strong and significant association between the two variables. It cannot conclude that one variable is a cause of another. Causation and association differ, meaning we are able to use statistical association between variables as evidence for causal relationship, but an association by itself is not proof that causal relationship exists. Bivariate relationships. Relationship between two variables is better understood through a bivariate table. Bivariate tables display scores of cases on two different variables. Independent variable x situated in columns and dependent variable y arrayed in the rows. There are three characteristics that shape measures of association. The first is existence. In order for measure of association to work, the association has to exist. An association exists if the conditional distributions of one variable changes across the values of the other variable. Conditional means that the values of one variable are dependent on those of another variable. With bivariate tables, column percentages are the conditional distributions of y for each value of x. If the column percentage changes, the variables are associated. If there is no existence of the association to begin with, then we cannot move forward to determine strength and pattern of an association. The second characteristic is strength. The strength of the association can be calculated by using three different measures. Phi, Cramer's V, or lambda. We will go into depth of each measure in the following slides. The third characteristic is pattern or direction. Direction is determined through percentages of the given formulas. The direction of an association can either be positive or negative. If an association is positive, the variables vary in the same direction. That is, in the positive association, high scores of one variable are associated with high scores of the other variable, meaning as one variable increases in value, the other also increases, and as one variable decreases, the other also decreases. In a negative association, the variables vary in opposite directions. High score on one variable is associated with the low scores on the other, and it increases in one variable are accompanied by decreases in the other. Visually, these relationships are expressed in a positive one or negative one to describe whether the association is positive or negative. The three measures of association. Nominal measures. Chi-square based measures, including phi and Cramer's V, and lambda.
Calculating phi. Phi is the easiest to calculate. Simply divide the obtained value of chi-square by the total number of cases in the sample and take the square root of the result. For a 2 times 2 table, phi ranges from 0, no association, to 1, perfect association. The closer to 1, the stronger the association. The closer to 0, the weaker the association. Calculating Cramer's V. For tables more than 2 columns and more than 2 rows, Cramer's V is implemented because it cannot be accurately measured through phi, as it's strictly used for measures of 2 times 2 tables. To calculate V, find the lesser of the number of rows minus 1, R minus 1, or the number of columns minus 1, C minus 1. We then multiply this value by n and divide the result into the value of chi-squared, and then find the square root. Like phi, Cramer's V has an upper limit of 1, perfect association, and 0, no association. Limitations of phi and Cramer's V. Phi or Cramer's V detect the strength and the relationship only. They do not identify the pattern. They cannot be used to compare the strength of the one relationship to another. Calculating lambda. Like phi and Cramer's V, lambda is used to measure the strength of the relationship between nominal variables in bivariate tables. can also be used to compare one relationship to another. Unlike phi and Cramer's v, lambda is a pre-measure and its value has more direct interpretation. Pre stands for proportional reduction in error, shows how much less error do you make in your prediction of the dependent variable y when you take into account the values of the independent variable x. Lambda tells us the improvement in predicting y while taking x into account. Lambda can be used to compare the strength of two or more bivariate relationships. To interpret lambda, E1 equals n, which represents the number of cases, minus the total of the largest row, and E2 equals, for each column, subtract the largest cell frequency from its column total and then add the differences together. The values vary from 0 to 1, where 0 is very weak and 1 is very strong in terms of association. Limitations of lambda. Similar to phi and Cramer's v, lambda can only describe the strength of the relationship and does not provide information about the pattern.
Now we will demonstrate how to do this on the SPSS program. We will have SPSS compute measures of association for the following case study. Does criminal victimization vary by area of residence? Click Analyze, then Descriptive Statistics, and then crosstabs. Move Life Vict, otherwise known as Ever Been a Victim of Crime, into the Rows box. Then move LUC_RST, otherwise known as Urban/Rural Indicator, into the Columns box. Click the Cells button and request column percentages. Click the Statistics button and request chi-square, phi in Cramer's v, and lambda. You then click Continue and then OK. The following output will then be produced. So as you can see, it is an easy procedure. The measures of association are reported below the output for the chi-square tests. 3 values for lambda are reported in the directional measures output block. Remember that lambda is asymmetric and will change value depending on which variable is taken as dependent. In this case, Life Vict, otherwise known as Ever Been a Victim of Crime, is the dependent variable, so lambda is 0, a value that indicates no relationship between the variables. Looking at the first block in the output, cross-tabulation, we see, however, that the conditional distributions do change, indicating that there is actually a relationship. The problem here is that the row totals are very unequal and lambda is misleading and should be disregarded. Phi and Cramer's v are reported in the symmetric measures output block. The statistics are identical in value, 0.106, as they will be whenever the table has either 2 rows or 2 columns. The measures reveal an association between the variables, although a weak one. The significance value of chi-square, 0.000, reported in the chi-square tests output block is lower than 0.05. So we reject the null hypothesis and conclude that the relationship between the area of residence and victimization is statistically significant. Even though phi and Cramer's v tell us that the relationship between the area of residence and victimization is rather weak, chi-square indicates that it is statistically significant. This reminds us once again that association and statistical significance are 2 different things. And that concludes our tutorial. Thank you for watching.